Hello there, Energy 301 students. Dr. Schragi here, and I'm talking to you today about how errors happen. How errors can happen in the hypothesis testing procedure and what we have to do about it and the risks that we take. Just to kind of keep us straight as to what we're doing so far. So far, in previous lectures in this module, we have talked about developing a pair of hypotheses. So we've developed like a null hypothesis and an alternative hypothesis. And in order to test that hypothesis, we developed a test statistic, also known as an inferential statistic. In the particular example we've been working with, we were talking about trying to test if the difference in the mean height, if there was a difference in the mean height of Creighton students versus the mean height of UNO students, and we used a Z statistic, which is a type of difference of two means type of statistic that you could find in a stats textbook or something like that. And this happened to be the statistic that we used. And the nifty thing about these kinds of statistics is that under the assumption that the null hypothesis is true, they follow a known distribution. In the case of the Z test, it is a standard normal distribution, the bell curve. And then we can figure out if the value of Z that we got from our observations was way out in the tail of the distribution of these, according to this known distribution, like the standard normal curve, we were able to find a probability that that was going to happen just by chance, and based on that probability, we were either able to reject the null hypothesis, we were either able to reject the null hypothesis, or we could not reject the null hypothesis. It was whether that the observations that we gathered proved to be inconsistent with the null hypothesis, because this result just seems so unlikely under the assumptions of the null hypothesis. Or we could not reject the null hypothesis because actually the data seemed to be consistent with what the null hypothesis was saying. So we have made a choice. We have either rejected or accepted, strictly speaking, we've either rejected or not rejected the null hypothesis, but the question is, was our choice correct? Or were there ways in which we could be mistaken? I don't mean as in like we didn't do the math right. I mean like we're wrong about the decision as to what these things mean. I mean, if I go back and I look here at this standard normal bell curve, and I compute some value of Z based on, say, our data of the different heights of Creighton students versus the average height of Creighton students and average height of UNO students, we've computed our test statistic Z, and we found it was some location along the horizontal axis on the standard normal bell curve. And if it was far enough out into the tail of the bell curve, we decided to reject H naught. But here's the deal, no matter where I put that, wherever that value of Z turns out to be on the curve, there's always going to be values of Z bigger than that can happen by chance too. Remember, this bell curve is showing us what the histogram of values of Z looks like under the assumption that the null hypothesis is true. And no matter how far to the right I go on that bell curve, it never gets all the way to zero. No matter where I am on that curve, there's always a finite probability that even under the assumptions of the null hypothesis, this could just happen. It could happen by chance. It wouldn't happen very often, but it could happen. And this is scary. Because see, here's the deal. If I'm going to be rejecting my null hypothesis based on Z's, let's say, weird value, sometimes that's going to turn out to be the wrong thing to do. Sometimes I just happened by bad luck to get a strange sample. My sample of N Creighton students, NCU I think is what the symbol we used was actually, my sample just happened to have a lot of tall people in it, or it happened to have a lot of short people in it, or same at UNO. Maybe my sample was just a little bit, by bad luck, well, I'm accepting or failing to, I'm rejecting or not rejecting a null hypothesis based on these samples and the Z test I got, but maybe I just had bad luck. Maybe I got a weird sample that isn't very representative. That's an error. That is something we want to avoid. We don't want to reject the null hypothesis if that's the wrong thing to do. Another type of error can happen the other way around too. What if there really is a difference between the two groups? I mean, our null hypothesis is that, the height of Creighton students and the mean height of Creighton students and the mean height of UNO students is the same, and then our alternative hypothesis is that they're different. Well, maybe there really is a difference, that alternative is true, but we don't end up rejecting the null hypothesis, and we say that actually they're the same. I mean, that could happen. Maybe you had some weird samples in which the two groups just happen to end up with relatively similar heights. This is hard to picture in the context of this business of heights of Creighton students and heights of UNO students because they're all adults and so on. Let's make this simpler. Let's talk about the mean height of 8th graders and the mean height of 4th graders. Okay? We want to test a hypothesis as to whether or not the mean height of 8th graders is greater than the mean height of 4th graders. But you know what? Just by dumb bad luck, there better be a difference, right? I mean, we really think that the 8th graders should be taller than the 4th graders. But here's the deal. Maybe I happen to get a bunch of short 8th graders in my sample. Or maybe I ended up to get some pretty darn tall 4th graders. And as a consequence, maybe my test actually worked out that I can't reject the null hypothesis that 4th graders are just as tall as 8th graders. Okay? That can happen. It's just a bad sample. But just by dumb luck, you didn't do anything wrong. You just had bad luck. And then you would decide, I can't reject the null hypothesis that 4th graders are just as tall as 8th graders, and even though that null hypothesis is clearly false. Oh, guess what? That's an error too. I'd like to avoid that problem. I really want to do the right thing. If the null hypothesis is right, I want to not reject it. If the null hypothesis is wrong, I want to reject it. In fact, if you kind of think about this as like you would in a logic class or something like that, there turns out to be 4 possibilities, which I'm going to kind of show you graphically here. I'm going to be making like a little graph over here on the right side of the screen, and I'm coloring in 2 areas of that graph. And we're saying all the possibilities of like how this test could play out are on this graph here. It's like a Venn diagram, if you're familiar with that term from like philosophy or logic or something like that. One possibility is that really H naught is false. And I'm going to color in that region in red. You'll see what this means in just a little bit. And maybe another possibility is H naught is true. I'm not saying I'm accepting or rejecting. I'm saying in the real world, God looking down from heaven could actually tell us H naught is true or H naught is false. Okay, I'm using data trying to figure that out. But there's a reality. Either H naught is true or H naught is false. But I'm either going to reject H naught or I'm not going to reject H naught, which I indicated by the shading. The shading that goes southwest to northeast is indicating regions where we rejected H naught, and the kind of shading that goes the other direction from like northwest to southeast is when we don't reject H naught. And you can see we've got 4 areas now. We've got areas where H naught is false and we rejected H naught. We have areas where H naught is false and we did not reject H naught, and so on, depending on whether based on their color and the striping I put on the area. There's 4 regions here, if you will, but this is sort of a Venn diagram. We're just kind of labeling possibilities here. Now, one of these possibilities, the one I have drawn with a black box around it here, looks pretty good to me. I mean, in that region, the red color is telling us, hey, these are situations in which H naught really was false, and that cross-hatching that goes from southwest to northeast is telling us that we rejected H naught. If that's labeling this possibility, hey, that's good. Hypothesis testing worked for us there. We had a hypothesis that really was false. We had no way of knowing that, and our experiment led us to reject H naught. Fantastic. Heck, I'm happy with this region that I have labeled with the black box too. Here in the blue coloring, we're saying that H naught is true. This null hypothesis is actually the reality. We don't know that yet, but we did our experiment and we decided not to reject H naught. Okay, hooray, that's a success. I'm going to label that one good too. That is a good possibility. That means that our hypothesis test worked. It led us to the correct decision. But there's other possibilities here that are less attractive. What about this one here that I have labeled with the black box there, where H naught is false, but the stippling going from northwest to southeast there tells us that we didn't reject H naught. These are situations where we said we're going to keep H naught, we're not going to accept the alternative, but the H naught was wrong. Okay? We have no way of knowing. I mean, the angels don't come and tell us that H naught is wrong. If angels came down and told us H naught was wrong, we wouldn't need this thing called science, right? We need to use our data to infer, to use reasoning and observations to decide for ourselves. But there's a problem. That's an error. If those things happen, if that combination happens where H naught was actually false, but we accepted it, or we did not reject it anyway, that's an error. And I don't like this possibility either, where it's blue with cross-hatching from southwest to northeast. Blue means that H naught is true. We don't have any way of knowing that because the angels don't come and whisper it in our ears, but we took our observations and we did our calculations, and the methodology of a hypothesis test tells us to reject H naught. We've made a mistake based on like a bad luck of a bad sample or something like that. Yeah, that's an error too. Uh-oh. There's 2 ways that these hypothesis tests can go right, And there's two ways the hypothesis test can go wrong. And that is very, very bad news. Now, this one over here that I have labeled where H naught is true, but we rejected it, that's what's called a type 1 error. And type 1 error happens when you reject a null hypothesis. I'm sorry, that is when you reject a null hypothesis that turns out to be true. That's a type 1 error, sometimes referred to, like especially in medicine and so on, as a false positive. Okay? It tells you that this is true. You decided to reject that null hypothesis, but the null hypothesis was right. Uh-oh. There's going to be a finite probability that that's going to happen, and the symbol that we're going to use for that probability is alpha. Anytime we run one of these experiments, there's going to be a finite possibility that we're going to do something wrong, just by the chance that not because we did the math wrong or anything like that, but because we got bad luck, and we draw a bad sample that isn't very representative of the group. There's the probability is alpha that we're going to come to make a type 1 error. We're going to reject the null hypothesis that is true. In the same way, we got this other region where there was an error. This is called a type 2 error. It's not rejecting a null hypothesis that's actually false. Okay? In the medical world, they call that a false negative, and you may have heard that term before as well. This is when, hey, we set up our experiment that Creighton students and UNO students were the same, testing their heights. Our null hypothesis was that they're the same height. Turns out that's wrong, but just because we got some students that weren't very representative of the students at Creighton, we ended up coming up with that they were the same height. That's a false negative. That is a type 2 error, and it's going to occur with a certain finite probability, beta. Every time we run a statistical experiment and we do a hypothesis test, the probability is beta that we are going to we're going to fail to reject a null hypothesis that's actually false. Oh my. This is bad news. We've got two types of errors, type 1 and type 2. A is the probability that you're going to make a type 1, alpha. Alpha is the probability that you're going to make a type 1 error, and beta is the probability that you're going to make a type 2 error. Man, I hate making errors. I really wish those statistics could help us avoid that. How is it going to... It was the statistics that led us to make the errors. It's the statistic that may have led us astray here. Let's think about how these things are going to happen. Okay, I'm going back to my diagram here of the standard bell curve. Type 1 errors, remember, occur when we reject a null hypothesis that's actually true. Okay, well, we're wrongly saying that our test statistic was far enough into the tail of the distribution. But here's the deal. How far is far enough? I mean, I labeled there with a black arrow a value of z about 2.3 or something like that. That's pretty far out there in the tail of the distribution. But you know what? We're in the tail of the distribution. In other words, values of z that come up that big are not that likely under the assumptions of the null hypothesis, but they happen. They happen a finite period of time, a finite number of time. Okay? Well, a way to avoid this problem would be say, what if I had a bigger value of z? What if I said my value of z has to be even bigger, like where I put that blue arrow? I put it farther out into the tail of the distribution. That has reduced the probability that I'm making a type 1 error, but there's still a probability. I mean, values of z as big as what I'm pointing at with the blue arrow there happen under the null hypothesis. Not often, but they do happen. There's still an alpha probability that I'm making a mistake here. I can't reject it. I'm going to reject this null hypothesis, but maybe I'm wrong. Or maybe this one, the red one, I'm way out there in the tail of the distribution. Turns out no matter how far I go out there in the tail of the distribution, there's always a finite probability that I have not gone far enough. That you will be making a type 1 error. You're saying, I'm far enough out in the tail of the distribution, this is a sufficiently weird sample that this is inconsistent with what the null hypothesis is telling us, when in fact, no, this actually happened under the assumptions of the null hypothesis, and we have made a type 1 error. The probability of this being alpha. Now, alpha turns out to be something that when you're designing your experiment, you typically set. When we are going to do our hypothesis test, we will often set alpha. A common number is to set it at 0.05, meaning you have a 5% chance of making a type 1 error. You're willing to accept a risk of 5% chance of making a type 1 error. This is going to be what we often say that like we are statistically significant at the 95% level. We're 95% confident that we have done we will be making the correct decision with regard to rejecting the null hypothesis. In practice, the way this is usually done, like in the case of our z-test, is you come up with like kind of a critical value of z that corresponds to a 5% chance of making that error. In other words, that p-value is 5%. then when you compute your test statistic, if it's bigger than that threshold value of z, you reject the null hypothesis. So just because it's kind of interesting to know. So like, for example, for that difference of mean type test, the value for a 95% confidence interval is z equals 1.96. So if the value of z that you get when you do your math of computing the averages of the heights of the Creighton students and the heights of the UNO students, if your value of z is bigger than 1.96, you can go ahead and reject that null hypothesis, but there is a 5% chance, there's at least the chance that you are making an error is not greater than 5%. At least the chance that you're making a type 1 error is not greater than 5%. Okay, so we can manage this. We can make some choices here that's going to influence the value of this alpha, the probability that we're making a type 1 error. Well, but alpha is just the probability you make a type 1 error. What about beta, the probability you're going to make a type 2 error? How does that happen? Type 2 errors, remember, happen when you are accepting a null hypothesis that you really should have rejected, because that null hypothesis is false. Well, let's say we have a value of z, we computed our heights of Creighton students, we measured our heights of Creighton students, we took their average. We measured our heights of UNO students, we took its average, and we came up with a value of z of 1.6. It's not really all that far out in the tail of the distribution. Are we going to reject h naught? Yeah, probably not. It's not really all that far out there in the tail of the distribution. So we're going to say that h naught is, we're not going to reject it. We're going to say that Creighton students have the same mean height as UNO students, but maybe that's not true. Maybe we just had a weird sample where those students weren't all that representative of Creighton students, or maybe they weren't all that representative of UNO students. Or maybe the difference between the mean height of Creighton students and the mean height of UNO students is real, but not that big. And so you don't really have enough information yet to prove that, this small difference exists. There's a finite probability of this, beta. That we're going to have said, yep, can't reject that null hypothesis, even though the null hypothesis, if an angel could come down from heaven and whisper in her ear and say, guess what, Creighton students really are taller than UNO students. Angels don't come and whisper in our ears. We're here to figure these things out for ourselves. And beta's our best choice. And we don't, in general, as a hypothesis test, we don't in general set the value of beta. Rather, beta is something you can compute based on the values of alpha and the sample size. And for every type of test statistic, there's a different way to get this beta. And it's kind of cumbersome and it involves a lot of weird notation and stuff. I don't want to get in the business of computing beta right now, okay? But it exists. A scientist could figure out this probability. And, well, rats. We're forced to pick a value of alpha. What is a level of risk we're willing to accept for type 1 error. And then based on our sample size and that value of alpha, we're forced to accept a certain probability beta, that is the probability of a type 2 error. That all sounds really grim. That sounds like we have a problem here. Is there any way we can work to avoid these problems? Well, alpha is kind of manageable, because we can choose to reduce the risk of a type 1 error. We could require that the test statistic be farther out along the horizontal axis, and therefore more out in the tail of the distribution, before I would choose to reject that null hypothesis. So, for example, for a difference of two means type test, which again is probably the most common type of statistical test, if you were willing to accept a 5% chance of there making a type 1 error in your results, the value of z works out to, as I've shown you before, 1.96. Or if you're willing only to accept a 1% chance that you are going to wrongly reject the null hypothesis and accept the alternative hypothesis, then you got to go way out there to z equals 2.57 in order to say, okay, at a 95% confidence interval, and 99% confident that I can reject the null hypothesis and accept the mean hypothesis. So yeah, I mean, we're in control of alpha. Alpha is something that the scientist or the engineer or the scholar gets to pick for himself or herself. We get to decide what level of risk for type 1 error we're willing to assign acceptable. But there's a catch. The farther and farther out I go on that horizontal axis, the farther out in the tail of the distribution I'm getting in order to reject the null hypothesis, the more likely I'm making it that I'm going to make a type 2 error. Because I'm basically, if I go far enough out there, if I require that I have to have a huge value of z before I'm going to go ahead and reject that null hypothesis, I'm almost certainly making the other kind of error. Because I basically made it impossible to reject H naught. Remember, type 2 errors is accepting H naught when it's not, or failing to reject H naught when it's actually false. Yeah, we can manage alpha. We can say, hey, you got to be way out there in the tail of the distribution. On the other hand, in order to do that, you're just making the risk of type 2 errors bigger and bigger and bigger because you're basically making it all but impossible to reject H naught. Oh no. See how there's a trade-off? There's no way to get around this, well, there's no easy way to get around this problem. You either accept the risk of type 1 error or you accept the risk of type 2 errors. There is always this trade-off. For a given sample size, you have a trade-off between alpha and beta. You either can make alpha big and beta small because maybe you're not willing to accept a type 2 error, or you have to make alpha small and let beta be big because you're not willing to accept a type 1 error. Whoa, this is really, really ugly. The only thing you can do to make this situation better is to take more observations. Only a larger sample can make this better, but no matter what, it's only making the situation better. This problem, this trade-off between alpha and beta always exists. But bigger samples do help. For example, if I just pull up again that test statistic that we've been using for comparison of two means, if you increase the value of the number of students that you sampled at Creighton or the number of students that you sampled at UNO, then that makes these two terms down here under the radical get bigger. I'm sorry, smaller. Right? As the denominators of those fractions get bigger, that fraction, those values there that I have circled in red, get smaller. Now, if we can make that whole denominator then get smaller and smaller and smaller, then this whole value of z is getting bigger and bigger. In other words, for a given calculated difference between those two averages, the average at Creighton and the average at UNO, we get a bigger value of z as n is bigger. So if we took our average of Creighton students and we found that their average was 10 centimeters greater than the average of the UNO students, that means a whole lot more if we measured 1,000 Creighton students and 1,000 UNO students than if we measured 10 Creighton students and 10 UNO students, right? This did not actually come as like a huge surprise, right? It should be clear that the more data we gather, the more certain we are of the results. So bigger samples help us get around this problem of alpha and beta, but you never really avoid it. Now, we could kind of work through some tortured example that wouldn't all be all that interesting, talk about this in terms of wind power or something like that. But you know what's a real-world application? Screening for diseases. Okay, let's talk about how a disease test works. You're going in to be tested for some awful disease, okay? Now, let's say you're the scientist, and you have developed a test that shows whether or not a person is going to have some particularly rare but very serious disease. Okay, there's lots of such diseases out there, and you might want to make a test that can help people know whether they have it or not. And, you know, like some genetic disease or something like that. And like medical tests, it can come up positive or negative. You either come up as you do have the disease or you come up as you don't have the disease. And like any kind of test or any kind of experiment, it can be wrong. Okay, sometimes this experiment is going to come up with the wrong answer. Let's talk about how alpha and beta play into this and to what decisions the people have to make. So each experiment that you run, each time you bring in somebody's blood and you run it through your machine that somehow tests whether they have that disease or not, you're really running an experiment where like you have written two hypotheses, and this can actually be done either way in terms of which one is H naught and which one is HA. For the purposes of what we're doing here, I wrote H naught to be that the person does not have the disease, and HA is the person who does have the disease. There's pros and cons to writing the hypotheses both of the ways here. But let me work with it this way. So what you're really doing, okay, now this is not exactly a statistical test, but it's a good example of how the scientific method encounters the same business of a type 1 and type 2 error. Although we could have done it statistically, and in practice there usually is. Usually they have gathered multiple samples or whatever. Okay, so you have two hypotheses. The person does have the disease, the person does not have the disease is our null hypothesis, and the person does have the disease is the alternative. You have to be really careful about this kind of thing when you're talking about diseases and life and death and getting treatment or not getting treatment. Because here's the deal. Telling someone they have the disease when they do not is a disaster. Okay, that is a type 1 error. We have wrongly rejected the null hypothesis. The null hypothesis was that they do not have it, which is correct, but we rejected it. And we told them they do. That's a false positive. If you're a doctor, you do not want to give people a false positive. But it's going to happen. It's going to happen at some finite probability alpha. Now, we might be in control of alpha based on like how we conduct the tests or how many times, whatever. I mean, there might be all kinds of ways in which we can control alpha. But it's going to happen with a finite probability alpha that you're going to tell somebody who does not have the disease that they do. On the other hand, telling someone that they don't have the disease when they really do is also a disaster, right? I mean, that's a type 2 error. You wrongly accepted the null hypothesis, or strictly speaking, you wrongly failed to reject the null hypothesis that they were healthy. Oh, you just let a sick person walk out of the doctor's office thinking they're okay. That's bad. That's a false negative. You also don't want that to happen if you're a doctor. But it's going to happen. Anytime they run the test, there is a finite probability beta that the test isn't going to work right. Okay, something's going to go wrong. There's something wrong with the sampling, something's wrong with the contamination or whatever. It's just like it's all analogous to what we're talking about, this beta in our statistical tests. This is a problem. And if you're a doctor or you're a researcher designing such a test, you got to make a choice here. Which is worse? Telling someone that they don't have the disease when they really do? Or telling somebody that they do have the disease when they really don't? There's a Sophie's choice for you, right? I mean, we don't want either of those things to happen, but unfortunately, that's the reality of every medical test you've ever had done, or your parents have ever had done, or your grandparents have ever had done. And in general, doctors have kind of come to a conclusion about this. In general, doctors want to make sure that nobody who has the disease is missed. They don't want people running around out there carrying some disease and not getting treated. Okay? So, in general, doctors have decided that telling someone they don't have the disease when they do is worse. We want to minimize that. Well, that is the risk of a type 2 error. Okay? They want to make sure that there is very, very low probability of a type 2 error, where they have failed to reject the null hypothesis, even though the null hypothesis that this person is healthy is wrong. Okay, so they need to design the test, the experiment, in such a way that beta, in this case, needs to be small. Okay, but like a statistical test, anytime in the scientific method, there's this trade-off between type 1 and type 2 error risk. If beta needs to be small, alpha needs to be big. Okay? Now, we can maybe manage this in terms of sample sizes and things like that, but no matter what, if there's a trade-off. The smaller and smaller we need beta to be, the bigger alpha's going to be. So let's actually work through some numbers here. Suppose we designed a blood test or whatever that is testing for some particular disease, and it has an alpha probability of making a type 1 error of 10% and a beta probability of making a type 2 error of 1%. Okay, that's a pretty small beta. We're saying that we are not going to make that error very often. Alright, so now let's say we screen 1 million people for this disease, and in reality, 100 people in that sample have the disease. Again, we don't necessarily know that we don't know that in advance. We don't know which 100 they are. Again, God doesn't come down, or an angel doesn't come down and whisper into our ear, these are the 100 people who have the disease. If we did have such a hotline to God's mind, we wouldn't need science. So we screen these million people. 100 of them really do have the disease, and 999,900 do not. All right, let's screen 1 million people. Well, of the 100 people who really do have the disease, 1% of the time we're making a type 2 error. We are wrongly failing to reject the null hypothesis, and we tell these people that they're healthy. 1% out of those 100 is going to walk away from the doctor's office thinking that he's healthy. Doctors hate that. Okay? Somebody's out there not getting treated for his disease. But it's worse. 99 out of 100 people are now getting treatment. But here's the deal. Of the 999,900 people who don't have the disease, 999,900 times 10% is 99,990 people are going to be told that they have the disease when in fact they're healthy. We have just told almost 100,000 people that they're sick when they're not sick. Holy cow. This is, of course, in the real world why doctors require more than one test, right? That you're going to come in for a second test or something like that. But here's the deal. In this particular scenario, 100,089 people came up positive for that test, but only 99 of them are actually sick, and one person who is sick walked away. I don't like this. I'm guessing that the doctor does not like the fact that practically every person he tells has got this disease is in fact healthy. Now again, they're really going to run a second test and all that kind of stuff to test on those people. That's why you don't just use a single test to make a decision about things like, high blood pressure medicine or some genetic therapy or something like that. It would be better if we could somehow make the situation better and not be telling so darn many people that they're sick when they are not. Okay, well suppose that the situation is that we've redesigned the test and now instead alpha is now 1%. There's a 1% chance of a type 1 error. And there's a 10% chance of a type 2 error. All right, we still screen 1 million people we don't know it yet, but there's 100 people who really have the disease, and 999,900 who do not. Well, of the 100 people who have the disease and come in and get tested, the problem is there's now a 10% chance of giving them a false result, false negative. 100 times 10% is 10 people. 10 people are going to walk out of that doctor's office being told they're healthy, and they've got the disease. Doctors hate that. Okay, they do not want people running around with some condition not getting treated. Of the 999,900 people who took the test and don't have the condition, we're still going to have this probability of type 1 errors where we're telling them they're sick when they're not. 1% of the time that's going to happen because alpha is equal to 1%. Well, that works out to almost exactly 10,000 people are going to be told they're sick when they're actually healthy. So we still have almost 10,000 people getting the wrong information. Well, overall, 10,089 people in this case test positive. But only 90 of those people are actually sick. And 10 of the people walked away being told they were healthy, and they're they're sick. If this is something that's contagious, they're spreading it. Doctors hate this. Okay? And the same is true. We could have worked through the same kind of thing, but we're talking about some other kinds of results where we're comparing 100,000 solar panels, or we're comparing. It's more personal when we talk about it in terms of disease. Okay, I think most of you students know that I have a son who has disabilities, and he has been tested for every damn thing. And lots of times things come back positive the first time, okay? And I wish I could tell you I'm enough of a cool-headed scientist that every time something comes back positive, I say, yes, but they're going to test it again. These are rare conditions. He'll be fine. And sure enough, that's in fact what happens most of the time is they test him again and this time he's fine. But let me tell you, I'm not cool enough about that. The reality is every time they tell me he's got something, I'm freaking out about it, as anybody would. And then it turns out he's fine. He's always fine when they test him for these kinds of rare genetic diseases and things like that. These kinds of errors are very personal to the people who these errors are being made about. In the case of medical stuff, it means people might be taking, well, first off, they're worried that they have a condition that the vast majority of them don't, and they might be taking medications they didn't need. If we're talking about decisions about things like, getting back to the situation of like electrical load and yield, we might be making bad choices about things like, management of the power grid, or how we're modeling the grid, or how we are working on alternative sources of energy. Errors suck. We hate errors, and there's just no way around them. But it is why we tend to talk, when we're speaking about science, in terms of things like confidence level or statistical significance. Okay? We can say things like the result is statistically significant at the 95% level. That means that there's no more than a 5% chance that we're making a type 1 error. Okay? In general, we don't go, yes, for certain kinds of things we do set it higher. Maybe we have a 99% confidence interval or a 99.9% confidence interval. If the risk of being wrong is so big, we might do that. But by and large, for most applications in science and engineering and so on, we generally want a 95 or maybe a 99% confidence interval, where we're accepting like a 5% or a 1% chance of making a type 1 error. But it sucks. It would be better if we could find ways to avoid it, but there just isn't any way. That's the nature of hypothesis testing. In our next lecture, what I'm going to do is I'm actually going to use that OPPD electricity data to do a demonstration of how we could do a hypothesis test on that data. All right, take a little break. Let me know if you have any questions. This has been Dr. John Schrage.